All right, so where we left off in class earlier today, I had gone through a couple of examples of predicting the sign of delta S, and we had a reaction that might be a little bit trickier to give us an estimation of its entropy change. Methane burning in carbon or in oxygen to produce carbon dioxide and water vapor. All right. A lot of this reaction happened in my house this winter, not because I had cows or anything like that, but I have a natural gas furnace, right? And so this is how my house was heated or how I cook at home. So this reaction happens all the time. Now I say that to give you a hint as about the spontaneous nature of this reaction. Okay, to thinking about the end game in here. But we're not quite there to think about the spontaneity yet. We still want to think about the entropy change. So we said this one was hard to predict the entropy change based on the lack of change, right? It's 3 total particles, 3 moles of gas, 3 moles of gas, all right? So remember that we earlier were able to define that the entropy of this perfect crystal was equal to 0. And that the entropy change was Q divided by T. If we couple these two ideas together, we're able to understand that every substance can now have a numerical value of S. Okay? So every substance can have an actual number for its entropy, rather than just kind of relatively thinking, how does this substance stack up against this substance, which we did with a couple of examples. This value we call the S0, the standard molar entropy. It's going to be the entropy at 25 degrees Celsius and 1 atmosphere. And these are listed in Appendix 2B in our textbook. Now, Appendix 2B is the same appendix with standard enthalpy of formation values. Okay? I'm going to change colors. I'm thinking the black might show up a little better just for the video. And if you remember, when we learned about these standard enthalpy of formation values, we used them in a formula that said the enthalpy change of a reaction was equal to the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. Hess's law, right? That's back in chapter 6. That was one way we had of coming up with the enthalpy change for a reaction. And we could do this because these were what are called state functions. All that mattered was what was the enthalpies of our products and what was the enthalpies of our reactants. Not how we got from one place to another, it's just the difference between the two. And it's what allowed those little things that I drew earlier today. So it allows us to, this is the mathematical calculation of that value right there. Okay? Well, entropy, standard molar entropy, is the exact same way. And so we have a version of Hess's law for entropy. That says the change in entropy of a reaction is just the sum of the standard molar entropies of your products minus the sum of the standard molar entropies of your reactants. So if I can go to Appendix 2B and look up the number for each one of these, I can just add up the numbers for my products and subtract the numbers for my reactants. And we'll get a numerical value for what the entropy change is, rather than just an estimate of positive or negative like we had before. Okay? So in Appendix 2B, here are the S0 values for these four substances. Methane is 186.3 joules per mole Kelvin. Okay. Oxygen is 205.2. Carbon dioxide is 213.8. And water in the gas phase, and you have to remember the phases of some things, there are multiples listed, so it's 188.8. So the entropy change of this reaction is the sum of my products, the 213.8 for CO2, plus 2 times 188.8 for water, minus the sum of my reactants, which are going to be 186.3 for methane, plus 2 times the 205.2 for oxygen. This equals negative 5.3 now joules per Kelvin, because remember the coefficients are moles. That's where technically the moles cancel out, so we're left with joules per Kelvin. So we see just ever so slightly a negative entropy change in this reaction right here. Okay? Now that negative would mean that that barely favors this reaction being non-spontaneous. But thank goodness it is a spontaneous reaction, right? And otherwise we wouldn't be able to heat it with heat our homes with it. You know, we'd have to use I don't know, you'd have to drive this reaction to heat your home. You'd have to use energy to make the energy to heat your home. It would be a waste to do it that way. Okay? So what to figure out, well, this says it shouldn't be spontaneous, so we still don't understand, well, why is it spontaneous then? Okay, so we haven't quite put that whole picture together yet of what makes a reaction spontaneous. All right. Let's do another one of these numerically. Okay. So another reaction, 2 iron plus 3 water vapor. So 2 moles of iron, which is a solid, plus 3 H2O gas. This is going to produce iron 3 oxide, so Fe2O3 solid, plus 3 moles of hydrogen gas. Okay. Before I give you the numbers, if we had to guess if there's an increase or a decrease in the entropy for this one, in other words, is it positive delta S increase or negative delta S for decrease, what would be the guess in this case, and why? Okay.
Decrease when there's more moles in the reactant side.
Okay, we got somebody says a decrease because we have more moles on the reactant side than the product side, and because 3 of those moles are gas, that's a wash. It washes out. We move from 5 different particles to 4 different particles. This side is, more organized, fewer options for arranging its matter and energy, right? So this is going to be the lower entropy side. Yeah, so I'd predict, just like you said, a negative change in entropy here. Okay? So even if you're going to do it numerically, it's good to make that calculation because it helps you decide is your answer right or wrong. Okay? Are you paying attention? But what I want to do is go to Appendix 2B now and look up what these S0 values are. Iron is only 27.3. Again, that's going to be joules per mole Kelvin. Water, once again, 188.8. The iron 3 oxide is 87.4. And the hydrogen is 130.7. So I got 4 values listed there and 4 down here, although water's in both groups. Notice that all of these are positive, right? When we did this with delta H's, I've erased it, almost all of our delta H values were negative, right? Okay? That's because the enthalpy of formation of a compound is negative. You're taking it to a lower energy state when you form the compound from the elements. But here, all entropies, all molar entropies are always going to be positive because they're all in comparison to the real zero, that perfect crystal solid. Just like on the Kelvin scale, all temperatures are positive, right? Because 0 is the end of temperature, the temperature scale. Okay, so you won't see any negative S zeros. Okay, delta S's can be negative, but S's cannot be negative. All right. So how do we get the entropy change for this reaction? We are going to add up our products. So our 87.4 for our iron 3 oxide plus 3 times our hydrogen 130.7. And then we would subtract 2 times iron, 27.3, and 3 times water vapor, 188.8. So, do all that, you get negative 141.5 joules per Kelvin. So this is a negative, as we predicted, a decrease in the entropy moving from the left to the right, primarily due to the loss of a particle, of a mole of material there. Okay. All right. Okay. So this would favor this reaction being non-spontaneous as well. Okay. But that's the rusting of the steam rusting of iron. And that'll happen as well spontaneously. So we've got two cases here of reactions that based on the entropy contribution, I would bet these things not happening, but they do happen, right? As I was saying earlier in class today, that's because entropy is not the only factor that we can and should consider. We also need to consider the enthalpy and then the temperature. Those were the three factors that come together. And it was Gibbs who figured this out and generated the formula for what we now call the Gibbs free energy. Although a different word to use in place of free might be excess energy, okay, or available. I think, James, you said earlier about something, being unavailable, okay? So what we're going to see is that in a reaction, you've got energies that are being put to different uses, and it was Gibbs who figured out how these pieces kind of go together. They work together or they work against each other in some cases, as it turns out. Okay? So if we take an exothermic reaction, just to review real quickly, right? Exothermic reactions. These are the cases where delta H is less than 0, where we're coming downhill. Right? They want to release energy. That's favorable from an energy perspective. We're always trying to take systems and have them get to the lowest possible energy level. They're lazy. They want to be down as far as they can in energy. So releasing energy favors your process being spontaneous. Okay? All right? Entropy, though, when we think about these entropy considerations, increasing entropy favors spontaneity as well. Okay? I guess I should write up here, this favors spontaneity. So it's sort of like opposite signs. A positive delta S favors spontaneity, and a negative delta H favors spontaneity. Okay? Now, delta H is an energy. Delta S, I went out of my way earlier in class to say, is not a form of energy, right? It's a ratio of energy to temperature. So if we take that ratio, though, energy to temperature, and we multiply it by temperature, bingo, it does become an energy that we can now compare to enthalpy. Okay? Let me give you a little analogy. Let's say I went and bought a scratch-off lottery ticket at Rutgers. and it was for the $10,000 game or whatever, all right? And I said, if I win, I'm going to give each of my students $100, right? So I win, and I get $10,000 payout to me. Hey, that's very favorable, right? And now I start subtracting $100 per student, okay? Well, in advanced chem, I have 21 students, right? So that'll be $2,100. So what's left over for me? Oh, $7,900 left over, okay? If I taught this course at a big school like a Penn State though, right? And say I had, 150 students in class times $100, that's $15,000. It's more than my $10,000, right? So I'm going to go in the hole, and have negative money left over if I win that scratch-off ticket, right? This is what's happening in chemistry. We have sometimes one thing that wants to give away energy, but then we're rearranging the system, and that might cost us, in the case of these two negatives that we just had a few minutes ago, that's like a penalty that we have to pay. For every degree of temperature, I'm paying this entropy price to reorganize my system. All right? Unless it's a positive entropy, then it's, going to pay us back as well. So this can work a couple different ways. Instead of me winning the lottery ticket, what if I get a speeding ticket? That's a negative. I've lost money. But everybody who I've ever loaned $5 to so they could go buy lunch or something comes and pays me back their $5. And you know what? I end up with more money than what I paid for the ticket, right? So that would be the case where we have like an endothermic reaction where it doesn't want to happen. That's me paying the ticket. But entropy is going to help out. By reorganizing the system and making it more spread out, we get a sort of a kickback, a payback in energy for doing that. All right. So we have to figure out how do we put these two against each other, and it was Gibbs who did this. So the Gibbs free energy, the change in the Gibbs free energy, delta G, is the enthalpy change of a process minus temperature times the entropy change. Okay? So here's where my lottery analogy really works, right? I get a payout here, but now I'm going to subtract per student, how many students do I have, and then how much money per student. This will tell me how much I have left over, or what's the available or free energy that this reaction has. Okay? The key to all of this stuff and connecting it to spontaneity is if delta G is less than 0, so negative. Now money we talk about being positive, right? I want to have money left over, be positive, but in energy it's the opposite, okay? If delta G is negative, the reaction is going to be spontaneous. If delta G is positive, the reaction would be non-spontaneous. And if delta G is 0, the reaction is at a condition of equilibrium, potentially changing from being spontaneous to non-spontaneous or the opposite. Okay? And this is a very important condition because we've talked quite a bit about equilibrium this semester. Okay? So that's what this Gibbs free energy is. It's sort of a weighing the main factors, enthalpy and entropy, against each other. But the entropy isn't by itself an energy. We have to take into account that temperature. Okay? And so sometimes it helps us and sometimes it hurts us. Okay? All right. So let's put this to work in a reaction here. So let's consider the reaction 4 KClO3s, which are a solid, decomposing into 3 KClO4s, which are a solid, and KCl, 1 KCl solid. Okay. Now, we could use Appendix 2b. I'll save us the time, but using Appendix 2b, we find that delta H for this reaction from the Hess's law formula, okay, adding up the product values minus the reactant values, is negative 144.1 kilojoules. And delta S for this reaction is negative 36.8 joules per Kelvin. So if I'm sort of just doing my thinking here about stuff, this favors spontaneity, the fact that it's exothermic, and this does not favor spontaneity. So what we're saying is actually moving from this side to this side, the right side is more ordered. And that's a penalty as far as nature is concerned. Somebody's got to pay that price. Somebody's got to do the work to organize the system on that side. So what we're going to do is we're going to use this energy here, right, to pay this energy cost here. And we're going to find out, is there any energy left over after we do that? You know, for this to be spontaneous. Will this reaction happen or not? Okay? So, delta G for this reaction then would be delta H minus T delta S. So that is negative 144.1 kilojoules minus, we're going to find, let's find this at, by the way, at 25 degrees Celsius or 298 Kelvin. We'd have to have a temperature defined. I didn't do that earlier. So it needs to be 298 Kelvin because our delta S has units of Kelvin in it. Now here's another little sticky point. Look at the units. H is kilojoules, S is joules. So we've got to make them equal before we combine them, right? In other words, we can't say, here's $20, and then somebody puts a quarter down and says that it's $25, right? That's a different scale. It's on the cents scale, right? It's a fraction of a dollar. These joules are a fraction of this kilojoule. So we have to combine or get them in the same unit set. So if I divide this by 1,000, it becomes negative 0.0368 kilojoules per Kelvin. We could have just as easily turned this into joules. It doesn't matter, but I'd already written that that was kilojoules. So, okay. So when this is all said and done, the answer is negative 133.1 kilojoules. This is a lot of leftover energy, right? We had 144,000 joules that we wanted to give off, and we had to pay $11,000 or 11,000 joules in tax. We still have 133,000 of those joules left over, right? So it's considerably high, the amount of free energy. And we would say this reaction is spontaneous at 298 or 25 degrees Celsius. Any questions on this formula so far? No? Okay. Now, this is very much like my little lottery ticket analogy, right? This is the case where, the first case, I can win like $10,000 and I have no problem paying out, you know, a small number of students this $100 per student, okay? But at what point does that no longer become to my advantage? Analogy here, at what temperature will this reaction no longer be spontaneous because we don't have enough to pay the entropy tax here? Okay, so that's a question we could ask, you know. So at what temperature does this reaction stop being spontaneous? Okay, Okay? Well, that transition will occur, right? The transition from spontaneous to non-spontaneous occurs when delta G goes from negative to positive. In other words, when delta G equals 0, that condition of equilibrium. So if we set delta G equal to 0 and use our T delta S, what we find is that, okay, delta H equals T delta S. So the temperature that this transition occurs at is the delta H divided by the delta S. And this formula is the transition temperature. It's how you can quickly find it for any, not just for this one, but for any reaction where you know the H and the S. This is how you find the transition temperature. So for our reaction here, we would take our negative 144.1 kilojoules, and we would divide it by the negative 0.0368 kilojoules. Again, I've converted it to that kilojoules so that the kilojoules cancel this time, not so that they add. Okay? And I get a temperature that is just really high. It is 3,916 Kelvin. So I want you to think of temperature as a number line, right? From 0 to infinity. This 3,916 that we just defined or just found is like a dividing line. This reaction on one side has one behavior, and on the other side of this line has a different behavior. Okay? Now we already know that way down here at 298, delta G was negative, because we had already, I just erased it, but we had already calculated the negative 133, right? So we can conclude for this reaction, it will be spontaneous for all temperatures less than 3,916 Kelvin. And then it will be non-spontaneous at all temperatures above. So once you find this transition temperature, you need a test on either side of that line to decide which range is a spontaneous range of temperatures. Okay? Let me do another example for you here. A reaction, just some generic reaction, has delta H equal to positive 72.4 kilojoules and delta S equal to positive 207.9 joules per Kelvin. For what range of temperatures is this reaction spontaneous? Okay? Over what range of temperatures, or in what range, is this reaction going to be spontaneous? Okay? So we'll start by calculating our transition temperature. T being delta H divided by delta S. So I put the H, 72.4 kilojoules, divided by the S. Converting it to kilojoules, it would be 0.2079 kilojoules per Kelvin. Step off my calculator here. 72.4 divided by 0.2079 gives me a transition temperature of 348 Kelvin. So now I want to draw this number line, right? 0 to infinity. And I want to put 3